and welcome to our presentation titled Deductive Verification of Realistic OCaml Code. This presentation has as a basis the work done by myself, Mário Pereira, and Simão Melo de Souza. So, we'd like to start the presentation with a sentence we found to be particularly well fitted to it, which is that programming is easy, but programming well is hard. And to fully understand why programming well is hard, we must first define what programming well means. Programming well means creating an efficient program and creating a program that does what it is intended. It will be mainly on the second point that we'll focus our attention today. That is because having an efficient program is useless if it has execution errors or if it gives the wrong value as output. So, given that, we can define three things we need to program well, and those things are a specification, which is a logic description of the computation to be done, here represented by what. We also need a program, of course, that describes how to calculate a supposed answer to an instance of the problem, represented by how, and, as a final ingredient, to verify the proposed program and that it does what it is supposed to do, we have to confront the program with its specification, here represented by why. We can see in this image that the specification and the program struggle between each other, and this is where the why part enters as a mediator, effectively confirming if the program and the specification are in agreement with each other. So, for the deductive verification of code, we use the tool called Cameleer, which has, as its main assets, the verification of programs written directly in OCaml, being that those programs are provided with a specification using comments in the specification language Gospel. The program is then translated to the verification framework Y3, being that it makes use of the Y3 IDE, presenting a more user-friendly experience by means of a GUI. This is a research prototype under active development. We'll now present a small example of a program written in OCaml with Gospel comments. Take this function, mem, which searches through an array of ints a for an integer m, returning a boolean representing the presence of the element in the array. A simple for loop through the array, and if we find the element we are looking for, an exception is raised. This exception is raised to ensure that the program is efficient, acting as a break statement in the loop. But, to verify the correctness of the program, we must provide it with a specification. We can see here that the specification is introduced using comments with a special character at, following the usual parenthesis and asterisk. We introduce in this function a loop invariant to guarantee that we are getting closer to the solution during each loop iteration, and a post condition, that if the function returns true, then there must be an I between 0 and the length of the array, where the element at index I is precisely the element we are looking for. Otherwise, none of the elements in the array can be equal to the element we are looking for. Calling Cameleer on the program shown before, we enter this Y3 session, where 6 verification conditions are generated, all of them being easily discharged using an SMT solver, such as Altergo, CVC4, or Z3. As for the workflow of the tool, we have seen that it takes as input an OCaml program commented with Gospel specification. If the program is compilable, that is, if it has no errors on the pure OCaml side of things, then it is translated to an YML file, and a Y3 session is started for that file, where we have the verification conditions of the function that can be discharged using the SMT solvers of choice, for example, Z3, Altergo, or CVC4. We decided to focus on answering two main questions, that were, can Cameleer be used in realistic examples, and do the design choices made in Cameleer work? To answer both of these questions, we decided to tackle the proof of the set module, which is present in the OCaml standard library, therefore being widely used. So, it should come as no surprise that the set module is a container data type and that it provides the usual set operation such as add, remove, union, subset, etc. This module is built on top of an AVL tree data structure, being the AVL tree a self-balancing binary search tree. The AVL trees in this module, however, have an interesting feature, that the balance factor used is of no more than 2, which is quite more permissive than the traditional balance factor used in AVL trees, which is of no more than 1. So, that being said, you might ask why 2? Well, using a balance factor of 2 proves to be more efficient in real use cases, effectively making a trade-off between the overall balancing of the tree and the excessive use of the rebalancing function. As for the signature of the set module, the module type order type represents the input signature of the functor make. As for the output signature of the functor make, it is here represented by the module type s. The make functor constructs implementations for any type, given a total ordering function compare. which should behave as the usual compare function in OCaml. So, for the data structure verification, we decided that a good example of it would be the ball function, because even though it is an internal function, it is of the utmost importance for the AVL trees. Assuming we have a call to ball of LVR, this function will create a new node with left on L, value V, and right on R, performing one step of rebalancing if needed. However, it is expected that L and R are AVL trees and that their heights differ at most by 3. All the elements of L must be strictly smaller than V, and all the elements of R must be strictly greater than V. Given that, the function returns a new AVL tree, where the element V has been inserted. We'll now show the specification of this function, written in a gospel comment. And, as you can see, it is not much different than the affirmations made in the slide before. Here, we introduce 4 preconditions using the requires keyword, where we say that L and R must be AVL trees, where their height must differ by no more than 3, that all the elements of L must be strictly smaller than V, and all the elements of R must be strictly greater than V. Given that, we introduce 5 postconditions using the ensures keyword, where we ensure that the resulting tree is an AVL tree, that all the elements present in L and R are also present in the resulting tree, and that V is also present in the same tree. We also ensure that if the resulting tree differs in height from the maximum height of L and R by at most 1, we also ensure that if L and R do not differ in height by more than 2, then the resulting tree will be the same as a call to the create function, which performs no step of rebalancing, effectively ensuring that the rebalancing step is really only done when needed. And because we believe a demo is worth 1,000 words, we will now showcase the verification of a function that uses ball.
Alright, so for this live demo, I've picked only a part of our proof of the set module from the OCaml standard library. Okay, and as expected, it features the functor make declaration together with the set data type declaration as well, and some gospel elements, like for instance, logical functions, okay, to be used in specification, lemma functions written in the form of OCaml functions, a predicate, in this case what it means for an element to belong to a tree, alright, the logical representation or the logical definition of the height of a tree, another lemma, and now the predicate that states what it means for a tree to be an AVL tree. It has to respect all of these conditions, right? Or just to be simply a binary search tree. I'll not go into many details about the gospel specification at this point. I'll focus mainly on the proof of the OCaml functions from the module set. Okay, another lemma function, and finally we get to the first actual function from the set module, right? A very simple one, the one that computes the height of a tree. So in this case, what you do is that in our gospel contract, we name the result of the function res, okay, and we state as a precondition that t, which is the name that we give to the argument of the function, t must be an AVL tree for this function to work well. And so we say that as a result, as a post condition, the value that the function returns is the same value as the one represented logically as the height of a tree. Okay, so this call here is to the logical function height and not to the programming function height. The two should not be confused. Next function is a create function. Okay, and together with this contract, the bal function, which performs one balancing step if needed. Okay, this one is much more interesting when compared to create. Okay, there's a bunch of cases and subcases. Right, it's gospel contract. And finally, the last one is the add function, which adds an element to the set. Add is actually contrary to bal and create is a function that is exported to a client of the set module, which means that you can call the add function, but you cannot call neither create or bal. These are internal functions. All right. So since we have the code, which is exactly the code that you can find in the OCaml standard library, annotated with gospel elements, right? We can now start our proof using Cameleer. And so this is as easy as typing Cameleer followed by the name of the module, in this case demo.ml. And we are immediately presented with the Y3 IDE, Integrated Development Environment. Okay, so on the left hand side you have your proof tree, and on the right hand side you have your code, the OCaml implementation and gospel specification. As you can see, I have already performed the proof of some of the auxiliary lemmas that I've introduced. Okay, so let's just jump ahead into the proof of the height function. Okay, this is a very simple one, as I stated. So now I can choose the task tab in order to inspect the verification condition that Y3 generated for the program that Camel here translated from the OCaml input program. Okay, and so the goal represents the verification condition that I'm trying to prove. All right, and above this line, I have all the hypotheses that are in my proof context. This is called a task in Y3 terminology, and this is exactly what is sent to SMT solvers. Right, so the goal for the create function is actually a very simple one. So for instance, if I choose directly the height node and I type here, let's pick CVC4 as our first attempt for an SMT solver, and you can see the green button appear, which means that SMT solver is able to discharge the verification condition for a height function, which means that the specification, or better said, the height implementation adheres to the its specification. Now, moving into the create function. All right, so this is a more interesting one when compared to height. I can take a look into the generated task, which I see that the goal is now a larger formula, but let's try to prove it directly as well using CVC4. Okay, and CVC4 is also able to discharge it in almost no time. So it is still doable directly. This formula here on the right hand side is still doable, still amenable to an SMT solver to directly discharge it. And now I can be brave and jump ahead into the bal function. All right, so now if I look into his task, now I see a huge formula as the goal. And so it comes with no surprise that the proof of this function is much more difficult, so it does not fit into this live demo. Let's just go take a look into very particular details of this proof. So the first thing that I do is to use the split transformation from Y3, which is going to generate simpler verification conditions from this huge formula. Okay, right, so you can see that now your task is easier, and in particular goal is much easier. Okay, so let's take a look, for instance, into this precondition 17. Okay, going back to the code. So in this case, the yellow part represents what I need to prove here. It's a call to create. All right, and so I see that I'm trying to prove the precondition of create that states that the element, or all the elements of the right-hand side tree, or the R tree that I pass to the create, this one here, all of those elements must be greater than the element v being the second argument of the function. So in this case, it is LV, right? So, which means that I need to prove that LV is strictly less than any element returned by this nested call to create. Okay, so if I take a look at this particular task for this particular verification condition, okay, let's go a little bit up in my hypothesis context, right? And I can see two hypotheses, H12 and H13, all right, that are still pattern matchings, and this means that I can still help a little bit SMT solvers doing some case analysis. For instance, a subcase of this proof would be when the R tree is empty, okay, and the other one when it's not. And also another subcase would be when L is the empty tree and when it's not, okay. So if I do another split here, I call the split transformation, I can now go into one of the two generated new verification conditions. All right, and for instance, if I go up, now I see that H12 is no longer a pattern matching, and now I see that I'm in the case, H13 is no longer a pattern matching, and now I see that I'm in the case where R is the empty tree, and the second one, with no surprise, states that, all right, it is not. so it's not the empty tree. So, okay, so I'm doing I'm helping SMT solvers doing some case analysis here. Okay, but still, I still have another pattern matching which I can split in order to make even simpler verification conditions. And when I get to that point, no more pattern matching in my hypothesis context, right? So at this point, it is very easy for SMT solvers to discharge these verification conditions. So for instance, I call CVC4 on the first one and Z3 on the second one, and they are able to automatically prove them. Okay, so remember that now we are in the case where L is not the, when R is not the empty list, right? So if we do now another split, we'll destruct the H13 hypothesis. Okay, so it's easy when L is the empty tree, but it's trickier when L is also not the empty tree. So in this case, I need to help my proof a little bit by doing an assert, all right? And this is a logical cut, okay? So what I'm trying to prove once again is that LV is strictly less than every element resulting from the tree after calling create, right? So in particular, I must say that X3, which is a renaming done by Y3, but X3, after some inspection of the proof context, you can guess that X3 is LV, right? So in particular, X3 or LV is strictly less than V. That's what I'm writing here as this logical cut. And so apparently this helps my SMT solvers to finish the proof, okay? So now let's go to the proof of the head function. Quite big formula, so let me do a split by pressing my S key of my keyboard. Okay, so now let me try to finish my proof using another SMT solver, AlterGo. Okay, so after some splitting, I see that there are a couple of preconditions, right, and some post conditions that are not discharged. Before trying to call a different SMT solver, let's take a look into what AlterGo was not able to prove by itself. So it says here that I'm trying to prove a precondition of a call to the BALF function using LL, V, and R. And so what is interesting here is that LL is now the result of a recursive call to head. This is important. Okay, and so what is the precondition of BAL that I'm trying to prove? I'm trying to prove that the difference between LL and R is at most, the difference between the heights of these two trees is at most 3. Okay, and so this is not provable at this point, given this specification, this gospel specification. Why? Because I also, since LL is the result of a recursive call to add, now I need to add a post condition that actually states something about the height of the resulting tree after calling add and the tree that is its second argument. Okay, so what I'm missing here is a post condition to this function. So I return to my file. So let me do a nicer alignment. Okay, so the post condition that I'm missing is actually this one. So I need to say that the height of a new tree differs at most by 1 of the height of the tree T that is passed as an argument. Okay, so I increase the height of a tree by at most 1 when compared to the height of T. Okay, so now if I can get back to the Y3 integrated development environment, and if I press Ctrl R, so it reloads my proof, so it calls Cameleer once again on the background and asks Y3 to generate a new verification condition for the new specification. Okay, so now let's try to select once again this node, the split VC, call AlterGo, and check if I'm able to prove the remaining preconditions. Okay, so it seems that he's pretty happy with me at this point. Okay, so the preconditions that I was having a hard time proving, now AlterGo is able to discharge them. Okay, so but the post conditions, that's not actually the case. Okay, so let me just inspect the task. Oh, okay, so I think I found the guilty one. This is a huge hypothesis in the form of a pattern matching. So if I select this node here I press S. Okay, I see that the other ones I was expecting these. The other post conditions are also huge, or have also huge hypotheses as pattern matching. So now let me call AlterGo on everything that is left. Okay, as you can see, now some of these post conditions are proved, only the last one remains. Let's take a look. Okay, you see the huge pattern matching here. So what happens after a split VC? Some of the cases still remain. So with no surprise, let me apply another level of split, and now I'll call AlterGo, and let's see what happens. So now everything is green, which means that the new specification of the head function, let me show you it, with this headed post condition is now proved by SMT solvers. So this means that the implementation adheres to the given specification. What is interesting here, and let me finish by stressing this out, is that in order to be able to prove this post condition, okay, we needed to add an extra post condition also to the BAL function, one that says that when there is no need for a balancing step, this function behaves as a create function. Okay, so it actually corresponds to this case here. Okay, and in order to do that, or in order to be able to talk about create inside the specification, since create is also a programming function, what we did is that we attached the logic attribute to the create function, which allows Cameleer, or which allows one to use the create name inside specification as well, or in other words, it also says that this is a pure function, side effect free function that you can use inside other function specification.
For the verification of the use of the data structure, we will approach the proof of the subset function. The subset function takes two sets and returns true if and only if the first one is a subset of the second. To define the correctness criteria of a function, we introduce the predicate subset. This predicate is only satisfied if, for all the elements present in the first set, then those same elements are also present in the second set. As you can see, this function grows through the two sets recursively, trying to find a match in the second set of the element we are seeing in the first one. Eventually, we reach the case where we have gone through all the elements in the first set, and therefore we return true, because we found a correspondence for every one of them on the second set. However, if we go through all the elements of the second set and not all of the first, then we know that there are elements for which we found no correspondence and must return false. As for the specification of this function, we introduce a precondition, where both the sets must be represented by binary search trees, and not necessarily AVL trees, because during the recursive calls to the function subset, we do not guarantee the balance factor between the trees. We also introduce a variant to guarantee that the function ends, here represented by the two sets, because the function effectively ends when one of them is empty. As for the post condition, we guarantee that the output is true if and only if the subset predicate is satisfied. Calling Cameleer on this function generates 13 verification conditions that, through some lightweight interactive proof, can all be discharged using the SMT solvers AlterGo, CVC4, and Z3. For conclusions, we'll first present the proof statistics, being that this consists of 122 lines of code and 117 lines of gospel specification. Calling Cameleer on the file, there are 21 functions to prove, from which 1,141 verification conditions are generated. All of these verification conditions can be discharged using the SMT solvers AlterGo 2.4.0, CVC4 1.0, and Z3 4.0.6. This proof can be replied on an average time of 53 seconds. As for the conclusion on the work, the road so far has been the successful verification of a module from the OCaml standard library. The proof is mostly automated, with very few lightweight interactive steps. Therefore, Cameleer seems well fitted for the proof of realistic OCaml code, and it is doable by regular OCaml programmers. The road ahead is proving other modules from widely used libraries, such as OCaml Graph, Base, Core, and Batteries. We also want to prove higher order iterators, starting with effect-free iteration, such as fold, and then moving on to effectful iteration, such as iter. Thank you for your attention. We'll be available to answer any questions you